Okay, sorry, I just had a misoperation last time. I accidentally ended the meeting. So let's start. So let's briefly review last lecture's material on MDP, solve MDP planning. So the foundation of IR is the Bellman equations. Bellman expectation equations, where you compute the expected value function, state value function for each state, or state action value function for each state action. Based on these recursive equations. So Bellman optimality equation computes the optimal state value function or the optimal state action value function. So this is the backup diagram. So for Bellman expectation equation, you back up from V pi S prime to V pi S. So S prime is the next state after you take an action. Whereas for the Bellman expectation equation and Bellman optimality equation for state action value function, you back up from the Q pi S prime A prime to Q pi SA. So you can think of there's a large tree growing from the initial state S and branching with the branching factor of the number of possible actions in S, followed by another branching from the state action node, the blue nodes, with the branching factor of the number of possible next states for the given state action pair. And then it grows further to a very large tree, and you just taking a portion of the tree. If you start from the state value function V, you get the Bellman expectation equation for V pi or V star. If you start from a blue node, the state action node, then you get the Bellman expectation and Bellman optimality equations for the Q pi or Q star functions. So Q state action value function contains strictly more information than state value function. So therefore, once you have the Qs, you can always get the Vs, but not vice versa. You can only get the Q from the V if you have the MDP model that is model-based IR. If you have model-free IR without the MDP model, then you cannot get the Q from the Vs. So policy evaluation is for a given policy pi, you solve the Bellman expectation equation for state value function V by writing out these V pi S equals a function of V pi S prime. So you can also solve for the Qs, QSAs, but in general, the V pi V functions, the variables are much fewer than the Q functions. So it's easier to solve for the Vs. because it's a known MDP, you can always go from the V to Q. So if you have a deterministic environment, you can simplify these Bellman equations for V's with this simplification. So if it's deterministic, then for a given state action pair, you have only a single possible next state S prime and the reward R. So the sum becomes a single term with a value 1 for the P term. So it simplifies into this. So for the first toy example of grid world, you have a random policy. So the agent wanders on the grid with no goal, no purpose. So you want to evaluate the value function for this policy. So the environment is deterministic. So if you want to move in some direction, you can move in that direction with 100% certainty. Unless you hit a wall, then you stay in the same position. So you can write out the V in terms of the average of all the possible actions. Here's the weighted sum of all the possible actions weighted by the probability of taking the action from state S. In here, the probability is equal in all 4 directions. So you always have 0.25 in front. And then you work out each Q for each of the 4 directions in each state. And you can get the V pi A as expressed in terms of the other V pi's. Similarly for V pi B and so on. So you have 4 equations, 4 variables. You can solve for it analytically. So you can see that this value function V pi B is the highest, 6.1. And V pi C is the lowest, 2.2. So intuitively, it makes sense because in V pi B, if you go right or up, you get reward of 5. So the B seems to be a very rewarding state. Whereas in C, wherever you go, you get reward of 0. So, but if you go further, so whenever the only way you get a positive reward is to go into state B. So the closer you are to state B, the higher the overall value of that location is. So you can see from the value function, it fits your intuition. So B has the highest value, A and D have equal and lower value of 4.2, and C has the lowest value. So this is an example, this is non-episodic. So the episode never ends. Next, we'll see some examples of episodic MDP. So the solving of the set of linear equations can be very time consuming, and you may run out of memory on your computer. So in general, you can use iterative policy evaluation So you have the set of four, say in this example, you have set of four equations. You can initialize all the v values to some 0 or some random value. Yeah, in this case, 0 doesn't work. So if you set all the initial v is to 0, then everything stays at 0 forever. So we can set up, initialize them to some random value, and so iterate through the equations, and eventually it'll converge to a solution. So this is the general way of solving the set of Bellman equations for computing the expected value for each state. So there's a threshold theta. That's when you decide that the solutions have converged. The higher the theta, the earlier you can converge. So here's an example. You're evaluating this MDP. It's episodic because now if you hit one of the terminal states, you exit the game and restart. So you can see that as you iterate through the game, through the iterations of the Bellman expectation equations, the influence of the terminal states gradually spreads throughout the entire grid. So initially, it zeros only affect the neighbor states, so 0.1 minus 1.7, and gradually it spreads to affect more and more states. And after many iterations, it will converge. So after convergence, you can imagine that the closer a location is to one of the terminal states, the higher the value function. Because every step costs you -1. So you want to exit as soon as possible. So therefore, the closer you are to the terminal states, the fewer steps you need to take. Therefore, the higher the value function. So a policy iteration adds additional step of policy improvement in addition to policy evaluation. So policy evaluation gives you the value function for a given policy, and then policy improvement generates a new policy based on the new estimated V pi by taking an argmax of the QSA. So this part is the QSA for the state action pair. So that's a greedy policy with regard to the current estimation of the V and Q value functions. So you perform evaluation followed by a greedy policy improvement step. So this is the example where you have a -10 in the blue states and -1 in other states. And the ideal policy should be pointing in this direction. So you want to learn that, but you are starting from a random policy, and hopefully after some iterations, it will converge to the optimal policy. So you can see that from the initial random policy, you have the very negative value functions. The farther away you are from the terminal state, the more negative your value function. Only after one policy improvement, you can see that the policies are generally pretty reasonable. So you're pointing into the terminal state. The arrows are in the right direction. However, the bottom row is messed up. Bottom row is pointing in this direction. So you need to fix that. So as you go through the policy iteration steps, gradually you are fixing the policies one by one. So now this policy is fixed. It's pointing upwards. If you go more steps, this policy is fixed. It's pointing to the right. And this policy is pointing to the right. And this is pointing to the right. So you can see that gradually it converged to the optimal policy. So you can think of the terminal state is the source of the reward. So its effect, it will gradually propagate throughout the grid. So after first iteration, it has propagated to cover the top half of the grid. But after more and more iterations, it gradually reaches the entire grid, so that every grid cell, every position knows that there's a very good terminal state in the upper left corner, and there are some bad states. These are the bad states, and they will learn to move towards the good state, 0, and while avoiding the bad states in the blue regions. So here's another example just to show that the policy converges much faster than the value functions. So that's why value-based methods are generally less computationally much slower than policy gradient-based methods. If you update the policy directly, oftentimes it converges much faster than updating the value function than taking argmax to get the policy. So the value iteration, it solves the Bellman optimality equation for optimal state value function until convergence, until delta less than theta. The difference between the values across iterations does not exceed a threshold. And then you simply take the argmax A over the obtained Q value function. So generalized policy iteration is a general form where you iterate for a given number of steps for value for policy evaluation, but not all the way to convergence, because that may be slow. But you simply run it for a fixed number of steps, and then do a step of greedy policy improvement, and then another round of policy evaluation improvement, and so on. So it turns out that even though you're not evaluating the policy until convergence, this kind of a sloppy approach still is guaranteed to converge to the V star, to the optimal V star and pi star. So that's very helpful to us in the computational, from a computational perspective. So here's a tool example. You have a single MDP with a single state S. with a single possible action A. So and then for policy iteration, you have the initial policy pi s equal A, and you compute the v pi is this equation. So sum over A is simply, this term is simply 1 because there's a single possible action. So you get the v pi s is 1 over 1 minus gamma. So q pi s is computed with this formula, which again is simplified into 1 over 1 minus gamma. So yeah, if you don't see that, maybe I should write it out more explicitly. R plus reward is 1 gamma over there's a single action from a state so so you get the q pi from the v pi, and then you do the policy improvement by taking an argmax A. The argmax of a constant, I mean, that means that any action is an optimal action. So the q pi is not actually a function of A. So trivially, you get the action A is the new optimal action, which is equal to the old action. So the policy is now stable. The policy iteration has converged in one step. So for value iteration, you compute V star. So max A is a single action. So max A does nothing. So you get the same result. Q star A, SA is the same result. So the optimum policy, if you take an argmax, again, is the same single action A, argmax of a constant. So in this very special toy example, both policy iteration and value iteration converges in one step, since V pi and V star is the same. It's 1 over 1 minus gamma, so it's a constant. And so subsequently, the q pi and q star are also constants. So the action is the same, a single available action. So it's just a kind of a silly small example to show the steps for the PI and VI. So I have this mini grid word example. So let me work through it. So this is a grid word with 5 possible locations. So all transitions have the same reward of -1. And A and D are terminal states with fixed value function. VA is -10 and VD is plus 10. So alternatively, you can think of as extra terminal state X with a Vx equals 0, and the only action in state A or D is exit. That leads to X with reward of A, RA equals minus 10, RD A equals 10. So the two views are equivalent. You can think of the actual terminal state, or you can think of the two terminal states with the value functions in them, defined as the VA minus 10, VD is plus 10. So you can think of the agent again having a very painful life. Every day it's alive, it gets a -1 reward, and so it wants to die quickly. But when it dies, it may go to heaven and go to state D, get a high reward, or go to hell and go to state A with a -10 reward. So the dark squares indicate obstacles in which the agent cannot move into. The discount factor is 1, so there's no discount for simplicity. There are two types of environments. One is deterministic, where the agent in any state taking action A, left, right, up or down, always moves to the next state in the movement direction unless it is blocked by an obstacle. Or it can be a stochastic environment. So agent in state S taking action A moves to the next state in the movement direction with probability 0.8, or to the left or right side, each with probability 0.1. So if it's blocked by an obstacle in any direction, then it stays in the same state with probability of moving in the blocked direction. So if it's blocked in the forward direction, then it stays in the same state with probability 0.8. If it's blocked on the side direction, then it's stayed in the same state with probability 0.1. So you can think of the robot has bad wheels, or the environment has strong winds that's unpredictable. So sometimes, even though the robot wants to move to the right, the wind or the wheel causes it to move in left or right direction, in different directions, but never backwards. So only forward or left or right. So let's do the policy iteration starting from a random policy. So the probability of going left or right or up or down is all equal to 0.25. And you have a deterministic environment. There's no stochasticity. Wherever you want to move, it will go into that direction unless it's blocked. So the set of equations, the V pi from C, you have 4 possible directions. You calculate the 4 actions and their associated Q value functions. So from C, if you go left, you go into B. So with reward of -1, so you have -1 plus the discount factor of 1 times the next state's value function V pi B. So if you go right, you have -1 plus VD, which is plus 10. if you go up, you get -1 plus VA, which is -11. If you go down, you get -1 plus V pi E. So if you plug in these terms, you get this expression for V pi C. So for B, if you go left, up, or down, you get you stay in the same state B. So you have the value is -1 plus V pi B. If you go right, you move into C. So you get the value of -1 plus V pi C. So similarly for E. So now you have 3 equations for V pi C, V pi B, and V pi E, and 3 unknowns. You can solve these equations and get the analytic solution of this -6 for C and -10 for B and E. So in terms of the backup diagram, from a given state S, you'll have branching factor of 4 because the agent has a choice among the 4 actions. From a state action node, you have a branching factor of 1 because the environment is deterministic. So you have obtained the value functions. Now you need to get the greedy policy based on the value functions. So from state C, if you you're looking for directions. So if you take action left, you go into state B. So you get a total value of -11. If you go right, you go into state D and get total value of 9. Similarly for up, which is -11, and down, which is -11. So you take the arc max among the 4 possible actions that maximize it. You take an action that maximizes the Q pi CA, which is obviously right. So therefore, the policy of in state C has changed from a random policy to a policy, deterministic policy, pointing towards the right. So for B, you can look at the 4 actions. Left, up, and down, you get back to state B, you cannot move. It's blocked in the 3 directions. So the Q pi B is equal to -11 for the 3 actions. But if you take the action right, you move into C, so you get a Q pi BR is -7. So taking the arc max, you get action right is the greedy optimal action. Similarly for E, up is the optimal action for the current value functions. So it looks intuitive, right? So in terms of the value function, the closer you are to D, the higher your value function becomes. C has a -6. And also in terms of the optimal actions, based on the value functions, you should try to move closer and closer to the good state, the D. So the closer you are to D, the better. So now we do another iteration. Notice here, our backup diagram has changed. The branching factor has changed from 4 to 1 from any state. Now you have a deterministic policy instead of a random policy. So from B, you have one single action to the right. From C, you have a single action to the right. From typo. Plug in from E, you have a single action to the is to up. So the environment is deterministic. So now you solve for the V pi for the deterministic policy pi. Now you have a single branch from state S, not 4. So you only need to evaluate Q pi CR, which is 9. For B, you have a single choice of R. So it's a -1 plus V pi C. For E, you have a single choice up. So it's a -1 plus V pi C. So we can solve the set of equations with 3 unknowns and get the solution of 988, which is equal to the previous solution of 988. Equal, so this is iteration 2. No, okay. So iteration 2 gets you these new value functions. 9 for C, 8 for B, and 8 for E. And then you do another round of policy improvement. So from say C, you look at all the 4 possible actions. Taking an argmax among them. So left you get 7, right you get 9, up you get -11, and down you get 7. So argmax is action right. Similarly for B, argmax is action right, and for E, argmax is up. So when you're doing policy improvement, you always evaluate all the actions and taking an argmax. Even though your current policy may be deterministic, you need to look at all possible actions, because the next iteration, your policy may change. But in this case, it didn't change. So it actually has converged. It's stable now. So based on, so our policy iteration has converged. We can finish and declare that the optimal policy is these arrows. So that's policy iteration for a deterministic environment, starting from a random policy and ending with a deterministic optimal policy. Now let's do the same, except for a stochastic environment. So the stochastic environment, remember that if you move in a given direction, you have 80% chance of going into the next cell, next position, or you may go left and go right with 10% chance each. So start from a random policy as before. Now look at the backup diagram. So from a state, you have a branching factor of 4, but from a state action node, you have a branching factor of 3, representing the 3 possible directions that the agent may move because of the environmental uncertainty. So because of the wind or the bad wheel, the exact direction from a state action node to the next state as prime is not determined by the agent. It's determined by the environment. So let's calculate Vpi C. So if you start from C and go left, you have 80% chance of landing in B and a 10% chance of landing in A or E. So this is the equation for your Qpi C left. Point A times Vpi B and 0.1 times Vpi A and 0.1 times Vpi E. So you know VA is a -10. It's a terminal state. So you can plug in that term to get -2 in front. So if you go right, you get this expression. So 80% chance of ending in D and 10% chance of ending in A or E. So you get 6 plus Vpi E. If you go up, you got this expression. And going down, you get this expression. So if you plug in all these terms into the Vpi C expression, you get this. So Vpi C as expressed in terms of Vpi B and Vpi E is neighbors. Similarly for Vpi B. So if you go left, you are blocked in the left direction. And also you are blocked in the top and bottom directions. So therefore, you will stay in the same position with 100% certainty. So it's Q pi BL is -1 plus V pi B. If you go right, then you have 80% chance of landing in C, but 20% chance of staying in B because a 10% chance up and 10% chance down, they're both blocked. So you stay in the same state B with 20% chance. So if you go up or down, you get blocked on the side, in one side. So therefore, you get blocked in the forward direction and also on one of the sides. So you get this expression. So for E, it's very similar to B. So after you get all the equations, you can solve the set of linear equations for the 3 variables and get the solution of this. So it's intuitive because the closer to state D, the higher the value function. Okay, any questions? So now you have the value functions, you do a policy improvement. So from C, you have 4 possible directions. You calculate the Q pi sorry, I think I made a mistake here. So the environment is not deterministic. So I should have similar equations to the this slide and calculate the probability of moving in the different positions. Instead of if you from C, if you go left, you may go into B or go into A or E. So yeah, it's a mistake. So let me see. Okay, 0.8 pi b. Let's work it out. Okay, I'll fix this later. So yeah, so policy improvement, you get a set of deterministic policies. So the policies should be okay. It should be pointing in these directions. So now you have a deterministic policy. You do another random policy evaluation. And now this is correct. So if you go right, you have 80% chance of moving into D, a 10% chance of moving into A, and 10% chance of moving into E. So you get a set of equations, and you solve to get the new value function for the deterministic policy, which is 6.5 5.3 and 5.3. These numbers should be right, because in the last slide, my mistake does not affect the value functions. And the policies should be correct. So another round of policy improvement. So yeah, I need to fix this. And but the result should be okay. So it should you should get the deterministic policy. So it has converged. You have found the optimal policy. So let's try value iteration for deterministic environment. So so now let's just recall our value iteration equation. So now we're looking at the max A over the possible next state and reward. This is QSA. So you cannot solve the analytical linear equations anymore for value iteration because of the max operator. So it's no longer a set of linear equations. So you must use iterative solving to get the solutions. So for deterministic environment, you have this branching factor on top from a state. You have a branching factor of 4, and from a state action node, you have branching factor of 1. So so you compute the Q value functions the same as before, except now for the V, instead of taking the expectation with the 0.25, the averaging of all the Qs, you take the max, which is equal to 9 for V1C. For V1B, you get the max of these terms. So the max, the best action is to move right from B. So notice we have in-place updates, which means that when we were computing the Q1BR, you need V1C. So if you're not using the in-place updates, you should use the previous iterations of V0C which is 0. So you get -1 plus 0, which is -1. So, and then the next iteration, you will get 8. So by using in-place updates, you use this V1C directly within the current iteration instead of the previous iteration of V0C. We're not using it. So this accelerates convergence. But if you did use the old V0C, it doesn't affect the correctness. You just need more iterations to converge. So this is called in-place updates. So similarly for V1E, we also use the current iteration's V1C value. So after the first iteration, you get 9 for V1C, and 8 for B and E. So the next iteration, notice that for value iteration, you don't have policy improvement. You're only updating the value functions because the policy is implicitly defined by the argmax operator. So you only get the policy explicitly at the very end after the Q value functions have finished, have converged. So for the second iteration, you get from C, if you go left, you get 7. If you go right, you get 9, up -11, and down is 7. So argmax is right. So from B, the argmax is right. From E, argmax is up. So after the after the second iteration, we have 9, 8, and 8. So value iteration has converged. So we have the V star, the optimal value function is equal to V2, the current iteration's value functions. So now you can take the argmax and get the optimal policy, which is shown in the arrows. So now let's look at value iteration for stochastic environment. So now the branching factors are from a state node, you get 4 branches for the 4 actions. And from a state action node, you get 3 branches for the 3 possible directions for each action. So from C, if you go left, you have 80% chance of landing in B and 10% chance of landing in A or E. So it's the same as before. So now you take the max action for the 4 possible actions, which is take the right direction and get the total value of 6. For B, you have the max over the actions is to the right with a value of 3.8. And for E, the max is 3.8. with the up action. So after the first iteration, you get these value functions: 6 for C, 3.8 for B and E. So now the second iteration, you simply repeat the process and get 3.68 for C and 4.86 for B and E. So again, we have the in-place updates. This current iterations of V is used in the calculation of the other Q value functions in the current iteration. So if you work out the steps, so this is a small program that returns the value functions across different iterations. So it gradually converges towards towards these values, which is 6.53 for C and 5.28 for B and E. So now you have the value functions. You can get the optimal policy by taking an argmax over the Q value functions, which is obtained from the V by the known MDP. We have the MDP small p of R S prime given as A. You can simply obtain the Q from the V's. So this is the process of value iteration. So any questions? So let's take a 10-minute break. Come back at 3:15 while I try to fix that mistake.
Excuse me?
Yes?
I had some problem with my sound, so I tried to ask a question, but it was I used wrong jack to connect loudspeakers actually, but that's better. I had a question. In this last slide, you actually assumed like delta is like a threshold is actually achieved, so we just then quit the iterations.
In the mini grid war example,
in the last step, you just like there is a very small change between the. And then you just you didn't explicitly said that, but you assume. I think I believe that it's assumed that it was below threshold, or maybe we limited number of steps.
Oh, actually, it converged exactly after 6 steps.
Okay, it wasn't shown, I believe, on the slide, but okay.
Yeah, I'll write it. It converged.
Okay.
Yes.
Okay, thank you.
Okay, we're back. So I just fixed the calculations on slide 48. So the calculation should be based on the branching factor of 3 from every state action node. Therefore, it should be updated to these numbers. So it doesn't affect the optimal action for the Q value functions. The numeric values are different, but the action, the directions are still correct. So from C should go right, from B should go right, and from E should go up. And then the next round of policy evaluation is correct. And next round of policy improvement. Yeah, this one I still need to fix, but I'll do it later. Okay, so I hope, yeah, and also here, the value functions converge. Yeah, there should be another iteration shown on the right to show that it has indeed converged. But I didn't show it, so. So that is the MDP planning for a known MDP. But in reality, you don't have the MDP. What do? You can learn the MDP using model-based IR. So you learn an empirical MDP model by estimating the model P R S prime given SA by executing the sum policy pi, maybe random, and keeping track of outcomes RS prime for each SA in the observed episodes. And then step 2 is to do the planning with the learn MDP and to solve for the optimal policy with value iteration or policy iteration. These are dynamic programming algorithms. So you have the acting to get experience, to train, to learn a model, and then from the model you do planning. So in control theory, this step is called system identification. But in reinforcement learning, it's called model learning. So here's an example for our mini grid world. Suppose you have you run the system with some maybe random policy, and you observe these 4 episodes. So episode 1 is BCD. Episode 2 is BCD again. Episode 3 is ECD. Episode 4 is ECA. So from this these 4 episodes, you can see 4 transitions from state action pair C and right. So for episode 4, from C, you're trying to go right, but you're unsuccessful. You actually went into A because of the environmental uncertainties. So for the same state action pair, C right, you have 3 you have 3 of them went into D, and 1 went into A. So you can get, and also the rewards are always -1. So you can get probability of getting a D from, say, C action R, and reward -1 is 0.75. And from CR going to A is 0.25 from these 4 episodes. Similarly, for from B taking action right, from B taking action right, you have these 2. So they all went into C. So you have 1 as the probability. And from C right, these 2 we just derived. And from D to an action exit, you exit. So with probability of 1 from A exit. So obviously in realistic scenarios, you have many thousands or millions of episodes, and you do an average, you can get a pretty accurate estimate of the transition probabilities. We just shown this small 4 episode example. So obviously these estimates may be wrong. These are empirical estimates. So, but hopefully with many episodes and many experiences, you can get a close to a truth estimate of the MDP. So that's it for this chapter on MDP planning. Any questions? So let's move on to the next chapter. Of a value-based IR. So now we have unknown MDP. So we need to perform sample-based learning. And this is now we're in model-free category territory. So we have been discussing MDP planning in the previous chapter. With known MDP, that is the transition from a state action to the next state and reward is known, you can do planning with value iteration or policy iteration. But now we don't have the MDP. We just learn the value function V or Q, and then take an argmax A to get the optimal policy. And then in the future lecture, we'll discuss a policy-based IR, where we learn the policy directly without using the value learning the value functions. So let's just recall our basic formulation of MDP. You have a state, a starting state, a set of actions, and transitions and rewards with a discount factor gamma. Now the model, the P is unknown. So so the state transition SA RS prime, the transition probability and reward is all unknown. So here's a simple MDP with a car So it's normally it's cool. If it drives slowly, it stays cool. If it drives fast, it may get warm or may not. If it's warm, if you drive fast, it will be overheated. And if you drive slow, you may stay warm or go back to cool. So if you go into overheated, you get a -10 reward. So so now the problem is that all these transition probabilities and rewards are unknown. You need to explore, perform exploration to gradually learn a optimal value function or directly the policy without knowledge of the underlying MDP by trial and error. So actually, this is the most realistic scenario because unlike the small grid world, in real life, the MDP is indeed unknown. So for example, autonomous driving. So from the current state, what is the state in autonomous driving? It's the physical environment, it's the traffic light, the pedestrians, other vehicles. So all these things are unpredictable. So next state, given the current state and action, the next state is not just dependent on your own actions. You know you accelerate, that's fine, but the traffic light may change in the next second. Another pedestrian may cross the road. So the outside environment is completely unpredictable. So therefore, the MDP is generally unknown.
I have a question. Does this mean that the environment is not Markov anymore because it changes all the time? So if you learn some policy, you have to relearn it because the model changes over time?
The environment is the Markov assumption is an approximate assumption. So I think I mentioned it before. The policy may be mapping from a current snapshot of the camera to your actions, or you may be mapping from a history of past 30 frames into an action. So the environment being unpredictable is not relevant to the question of MDP, right? So suppose for NVIDIA-NET, their end-to-end driving system maps from the front camera view into steering or braking acceleration actions. So assuming that assumption is correct, it doesn't matter if the environment is unpredictable. I just map from the current picture to my current action. So it's an orthogonal issue. As for Waymo's ChauffeurNet, they think that the current image is not enough, so they take a history of past, maybe 25 or 30 frames, and use map that into, from that map into the actions. So in either of these cases, they're not predicting the future. They're just making a decision based on current image or current plus past. So that's why they are model free, because model based is infeasible. You cannot possibly learn the MDP for autonomous driving.
But if the environment changed, then you need to have another policy, or?
No, the policy is not dependent on the future. It's only dependent on the current and the past.
Yeah. Okay.
Yeah. Just one thing, Carlo, you need to fix your sound again.
Oh, sorry. It seems to forget things. No, I hope it works. Thank you.
Yeah, so
James had a question, I think.
Yeah, in some robotic tasks, they actually use model-based RL by learning the model. For example, if you're pushing an object, and if you issue a action push, and you know the object's current position, you can predict the object's next position pretty well. So you can build a model of the environment maybe at the pixel level. So given the current image, you can predict the next image. And then you do planning based on the MDP model. So that's actually possible for simpler environment with pushing objects with a robotic arm. But for driving on the street, that's not possible. So for RL, there's no supervisor, only a reward, unlike supervised learning. And reward may be sparse. That is for chess or Go, you may get a win or lose decision at the very end, or it may be dense. For example, for autonomous, for the driving scenario, we had a toy example where at every instant you get a reward based on your cross-track error and your heading direction. So feedback may be delayed, not instantaneous. And you have a sequential non-IID data identically. So IID data is when you have supervised learning, every input image is independent of the previous image, say for MNIST classification. Any input is unrelated to previous and past inputs and future inputs. So that's IID. But for RL, the agent's actions affect the subsequent data it receives. If you issue a left action, you will see the images from the left direction, which is different if you issue the right action. So it means that the input data are all correlated. They're not independent from each other. So for model-based IR, you learn the MDP first, then solve for the optimal policy with policy iteration or value iteration. But for model-free, you learn the policy without learning the MDP first. So here's an analogy, not a reinforcement learning problem, just a simple analogy. So suppose you want to compute the expected age of a group of M students. So if you know the probability of the distribution, the probability percentage of students with a certain age A, that is the P. A is a random variable. Capital A is a random variable. Small a is the concrete value of the random variable. So you can compute the expected average age by a weighted sum like this. So you know 35% of the students have age 20 and so on. So you can simply do this weighted sum. But without knowledge of PA, that is, you don't have the model, you can do either model-based, that is randomly sample a number of students, n, less than m, and ask for their ages in order to build an estimated model p hat. where num A is the number of sampled students with age A. Then you use a p hat to compute the expected age. So estimation of p hat by sampling and take expectation over the empirical estimated p hat. Or if it's model free, you randomly sample n students and ask for their ages and then compute their expected age directly, taking a average over all the AIs. So for IR, the idea is similar. You simply replace the capital PA with the MDP model. So why does model-based work? Because if you sample enough, eventually you will learn the right model, the right percentage of students in each age group. And if it's why model free works, it's because the samples appear with the right frequencies if you sample uniformly. So here's a illustration. So the random variable capital A denotes a student's age. If you knew the student, the group consists of two age groups, 20 and 22, with ground truth distribution of equal probability of being 20 years old or 22 years old. Then you can compute the expectation of A as the weighted sum of age, which is 21. But in general, the ground truth distribution is unknown, so you must estimate. So if it's model-based, you randomly sample n students to build an estimated model p hat. For example, p hat age 20 is 60%, age 22 probability of 40%. Notice that this estimate is different from the ground truth distribution of 50-50%. And then you use the estimated p hat to compute the expected age, which is 20.8. Not exactly correct, but it's the estimate. So if it's a model free, then you randomly sample n students and compute their expected age directly. So for example, you sample 5 students with ages 20, 20, 22, 22, 20. And then you do a simple average to get 20.8. So in this simple example, these two approaches actually gives you exactly the same results.
Excuse me?
Yes.
I'm not sure whether I'm the only one, but I really don't see the difference in the calculation, because you are using exactly the same things, just call it differently.
Yes. So they gave the exact same results.
But I mean, I'm not. I mean, I say that it's the same result, but I mean, the procedure to calculate it, you just call it differently, but it's the same. Exactly. I mean, all the steps are the same.
Yes. for this calculating average, these two approaches for the same sample n samples, it'll give you the exact same results. However, for model-based IR, the idea is that you learn the MDP model from the data. So MDP model plays the role of the P, capital P. So in the IR case, so if you, for example, in the grid world example, if you learn the model, MDP model first, and then do planning as we did just earlier, or if you directly learn a value function or the policy from data without learning the MDP model first. And then for the small grid world examples, they should give you the same value functions and policies.
What it's okay. I mean, I understand the principle, but the example is actually not demonstrating the difference because you are doing exactly the same calculation, but just call it differently. But it's okay. We don't need to spend more time on it.
Yeah, let me think. How can I say this better? Model. So sufficient samples So in that sense, it's similar, right? They should get the exact same results. Yeah. So yeah, given sufficient samples, sufficient exploration in IR, model-based and model-free should not make any difference. But sufficient samples may mean many millions or hundreds of millions of samples for large systems. So in general, you may not have sufficient samples. In general, model-based IR has much better sample efficiency. So that is, it needs fewer samples to get an accurate result, while model-free IR needs a lot more samples. But ideally, given infinite or many billions of samples, they should get identical results. Yeah. Let's start from Monte Carlo methods, and then TD learning, and then stars on Q learning, and finally function approximation. So Monte Carlo methods. Let me see. We have a few minutes. Should I go forward?
I have a question regarding the bonus assignment.
Oh, yes.
So when will you publish it?
So the idea is that you should have self-defined projects. I assume that in your work or in your own personal interest, you should have a preferable project you want to work on. So work on your own project and submit it. I may provide a few suggestions, but they're only suggestions.
And what are you expecting there? I mean,
I'm expecting the source code and also a report describing the project and why it's interesting. So, for example, you may work on the highway environment and come up with some better algorithms, or you may even work on some projects that's not exactly related to autonomous driving, as long as it's related to in some way to some aspect of the course, maybe object detection, or maybe segmentation or reinforcement learning applied to some other domain that you are interested in. So I'm pretty flexible as long as you send me email beforehand on your topic and I approve it. So as for the deadline, I'm thinking you can turn it in before August should be fine. So it's strictly optional. It's an actual 10 points. Without it, you can do pretty well on the course. It's just that if you're interested in these topics and you want to work on something else, then you can work on it.
yeah, thank you. I think it sounds like a good idea, and if till August, so we have also some time.
Yeah.
Yeah.
So did anyone start on the lab on the highway environment? Did anyone try it?
I already submitted my solution.
Oh, okay.
I hope I did correct.
There's 2 submissions, so I had a look at them already, so but I collect some more to make a batch of it. So good luck, you other guys.
Okay.
One thing regarding whether you should continue today or not, I would prefer your lectures to be as early as possible, so we have some time to, like, before the exam.
You want me to finish all the lectures so you have some time to review the material?
Yes, of course. Yeah. Thank you.
Yes,
but
yes.
If it is possible, but if not, it's. I mean, because you said maybe there is a short time today to continue, but for me, I'm not sure. You can ask the others, but if you have time and nobody complains, then I would prefer to continue today.
Yeah, we should. I hope you can finish the materials, but we don't have to finish everything I put on the website before the end of the term. So I can actually I will. For the L8, I think I'll simplify it. L8 is basically discussing research papers on the different approaches to autonomous driving with reinforcement learning or imitation learning. So I think I may simplify this lecture.
Just to be clear, I really don't want you to simplify things. I'm here to learn things. So if the choice is simplifying things, that so you just like we finish it earlier, then I prefer to make it complete, but even if it takes time.
Oh, okay. I'm glad to hear that. So Nimad, right? So yeah, so many students have received complaints that they are burned out. They feel there's too much material, but also there are students who are eager to learn. I mean, but I think the students from burned out shouldn't be too worried because, you know, the exam is just open book. Even if you may not fully understand something, you can always look up. But for these calculations, I think I made them pretty clear. I hope you can give it.
I mean, it's like this. I had a problem with the sound again, but it's Nenad. But anyhow, even if you make it more complex, it doesn't. I mean, you can choose to include it in the exam or not. But I mean, knowledge for me, knowledge is more important. So.
Oh, I'm very glad to hear. Yes, yes, yes. Okay, let's do maybe some 30 or 40 minutes more today and finish later. Actually, I wanted to show this video from last year because I think I did a pretty good job in the last year's this parts lecture. So let's watch this lecture for, I don't know. Let's see, okay.
Can I take a question quickly before we watch?
Sure.
I've been thinking, I mean, I've watched different simulations for reinforcement learning, and what you see in the simulation, you make a lot of mistakes. Let's say for the car autonomous, you crash into a lot of things and you start to learn from that. And I've been thinking, does that really actually work in a real life scenario? Like if you're training a reinforcement learning for autonomous driving, and how does that compare with imitation learning? Because I mean, if you need to crash into a lot of things before the agent will learn well, is that really a very optimal situation to be in?
Well, that's why you need simulators like Carlo or a number of other simulators.
Yeah, but then usually you need to also account for, you cannot really actually simulate every behavior that you encounter in the real life traffic, right?
Actually, you can simulate most scenarios. In fact, simulation is more powerful because if you're on the road, you're likely to be driving without accidents. You're less likely to get into corner cases, strange, difficult cases. But in the simulator, you can artificially generate very difficult driving scenarios, which is not feasible in real life. So, okay. So that's why there are research work on solving some optimization problems and generating very strange and difficult scenarios just to train the autonomous vehicle. So are there any cases that you cannot rely on simulation? You must train in the real world. Yes, but maybe more in other domains like drones. So if you're training a racing drone, there are drone races with obstacles and drones flying at a very high speed. In these cases, the aerodynamics of the drone can be very complex, too complex to be simulated accurately in the simulator. Therefore, you need actual physical experiments to train the agent. So in these cases, you may have the concern of crashing the drone during training. And that's indeed a valid concern. Whenever you are training in the real physical world, your risk of damaging the environment or damaging the vehicle is there. So the solutions are that first, you may make your vehicle resistant to crashes. So there are designs, special designs for drones that are safe to crash. You may put some kind of surrounding, some kind of things around the drone so that it doesn't damage after crashing. Or there is a branch of reinforcement learning called safe reinforcement learning. That is, you place some safety guards at runtime so that whenever something dangerous is about to happen, the safety guard kicks in and corrects the vehicle so that it doesn't crash, so that you can learn without crashing. So there are different approaches. But in autonomous driving, in fact, so for example, Waymo, they have the most miles driven on the road among all the autonomous driving companies. Well, maybe Tesla has the most, but in terms of L4, high levels of autonomous driving, Waymo has the most miles. So, but they have many, many more miles driven in the simulator.
Does any of them use reinforcement learning, or they use imitation learning, or other approaches?
They use all kinds of learning. So, so for vehicles in production, like a Tesla, they only use deep learning for perception, and traditional planning and control algorithms for the other stages. But for end-to-end learning with reinforcement learning mapping from pixels to action, to actuation, or from pixels to plan, many companies are doing it in research, like Aurora, like Waymo, like a few others. But these are not as mature as the classic planning and control algorithms. So I think they're not really used in production. They're only used in experimental vehicles as of today.
Okay, thank you.
Yeah. So let's watch it for maybe some time and see how far we go. Prediction first and control. Prediction is just policy evaluation. So consider episodic tasks for MC-based prediction, where you have a finite length episodes and value of a given state for policy pi is to start from the state S and taking actions based on pi and counting the cumulative reward, denoted as a GT, with the discount factor gamma. To estimate V pi S or Q pi SA, you can get all trajectories containing particular S or SA and compute the cumulative return for each trajectory starting from S or SA and average over all trajectories to get expectation. So at every state, so each circle is a state, you have a branching factor. The branching could be due to policy, could be due to environment. So, and then you a specific episode is a path from start to end of the episode through this a tree of possible next states. And as you can imagine, if the branching factor is very large, these possibilities, possible paths, the number grows exponentially. So you may need many samples to get accurate estimate due to random policy and stochastic environment. So I think the early chess playing game that beat Deep Blue, that was based on Monte Carlo method, where they simply well, it's exhaustive search, not really Monte Carlo. So they are more brute force. Here we're, if you're sampling many trajectories starting from a state and averaging to get the value function, this is Monte Carlo. But if you're exactly trying all the possibilities with no sampling, that's exhaustive search. So here's MC prediction. There are two variants. One is first visit, where state S may be visited multiple times in the same episode. So if it's first visit MC, then you estimate V pi S as the average of these returns following first visits to S. If it's every visit at MC, then you average the returns following all visits to S. So the figure shows the every visit MC. So initialize the VS arbitrarily and typically all zeros, and loop forever, generate an episode following the policy, and you go backwards from the last non-terminal state st minus 1. St is the terminal state. So starting from st minus 1, you accumulate the rewards, adding a discount factor, and do an average over the past returns from state st. So the average could be done with a running average. So here's an example. This is an episode where you start from the left and going until to the right until you hit the terminal state. So you work backwards. The 1, 2, 3, 4, 5. Yeah, this guy is 5. G5 at this point, its reward is. Did I miss something? I think I forgot to. Oh, okay. The edges are labeled with the rewards on every transition. So okay. The last one is 5. G5 is 0. The next one is G4. It's reward 2 plus. That's the only reward of 2. And G3 is 1 plus gamma times R5, which is G4. That's 1 plus 1. And G2 is R3. That's 7 plus gamma times R4. That's 0.5 times 1 plus 0.25 times 2. You can do the computation this way, or you can plug in G3 for this latter term as G3. So by working backwards, you can do less computation. If you go forward, it's fine. If you go forward, you just simply recompute everything at every step. But if you go backwards, you can reuse some of the computation. So that's why in the pseudocode, you go backwards. So one problem is exploration. So we have learned epsilon greedy before, or epsilon soft. So for stochastic policy, where you take the current optimal policy with probability 1 minus epsilon, and epsilon is for exploration. But if you have a deterministic policy, you cannot have epsilon greedy. So the way to do exploration is exploring starts. So for example, in this grid world, you have the deterministic policy, but it may not be optimal. You want to improve it by doing Monte Carlo. You want to evaluate the Q value at every position. So you can specify that the episodes start in S0, A0, the blue state, and every possible essay has a non-zero probability of being selected as the start. And from S1, A1, follow policy pi for action selection. So the first is the blue S0, A0, because you wanted to compute its Q value. So you take the first step, the blue step. Then afterwards, you follow the current policy, the red arrows. So by placing the initial starting point of every episode randomly on the grid, you can do exploration, even with a deterministic policy. So this is the actual execution of this episode. So that's for MC for prediction. For MC for control, this is the previous slide on policy iteration, where you have policy evaluation followed by policy improvement. Now with MC exploring start, you can do generalized policy iteration. So after every episode, the observed returns are used for policy evaluation. And then the policy is improved at all the states visited in the episode. So generate episode following policy pi, a loop for every step of episode. Going backwards, you update the returns and perform average to get the Q, and immediately you take arc max of the Q. That's every step of the episode. So that's not evaluating Q to convergence. That's more like this. So you are doing very fast. One step compute update of Q, and one step arc max A over the new Q. So so it lies between two extremes. The policy iteration we learned before, the policy evaluation must achieve convergence up to some level of approximation, the theta parameter. For value iteration, only one iteration of IPE is performed between each step of policy improvement. But here, we are performing the the policy evaluation in an episode by episode basis. So here's one example. So you have an agent initially in this one-dimensional grid, the uniform random policy of going left or right. So in one episode, it wanders around until it hits the goal and gets a reward. Then the QSA for all the states visited in the episode are updated, and the policy is improved based on the argmax QSA. So the figure shows that only one state's policy, this guy, is improved, but in general, it's possible that multiple states' policies are changed. So after sufficient exploration, all states' policies may converge to the optimal pi star, that is pointing right towards the goal, the cheese. So if some states are not explored enough, for example, if the leftmost state is never visited, or it's visited only a few times, and the updates to the queue is not enough to overcome a bad initialization, then its policy may not be optimal. So sufficient exploration is important for converging to the optimal policy. So let me clarify a little bit for this example. So the slides I updated. So in this case, the agent starts from state S, this state, and happens to go right to hit the goal. Then only the value, the policy of state S is changed. Only this policy is changed. But in general, policies of all states visited in the episode are updated. So if you start from this state and you move right and hit the goal, then all the 3 states policies will be updated. So yeah, just to clarify. So epsilon greedy, we saw it before. So it selects a random action W with probability epsilon. Select the greedy action, which is the argmax. Yeah, greedy action. Argmax with probability 1 minus epsilon. So with a total possible actions in state S, select each non-greedy action with probability epsilon divided by the size of the set. The greedy action with 1 minus epsilon plus epsilon divided by that. So the because the random action includes the greedy action as one of it. So for epsilon greedy, you have equal probability for all non-greedy actions. But for epsilon soft, it only has a requirement that every policy A is selected with a lower bound probability, but it may have some other distribution instead of the equal distribution for epsilon greedy for non-optimal actions. So it's a more general form of policy specification. Epsilon greedy is a special case. So you may think of a softmax with additional lower bound, for example, could be a soft policy. but just the soft max doesn't give you a lower bound on the probability. So the optimal epsilon soft policy or epsilon greedy policy is the highest policy, best policy with the highest value in each state among all epsilon soft policies. So in general, it performs worse than the optimal greedy policy pi star. So in general, the greedy policy with the optimal value Q value function is the optimal policy. So if you add epsilon soft to it by having some exploration, the resulting policy is worse than the greedy policy, deterministic policy. Worse than the optimal greedy policy. This is deterministic. So by optimal epsilon soft, we mean that it is optimal among all epsilon soft policies. But if you expand your view towards all possible policies, then it's generally worse than the optimal deterministic policy. So here's the generalized policy iteration. We saw GPI with Monte Carlo for exploring starts. Now we see we're not using exploring starts. We're using epsilon soft policy. So first, the policy is not deterministic. It's epsilon soft. And then there's no exploring starts. You can start from fixed S0. So in the previous, we must choose S0 randomly, such that all pairs have probability higher than 0. So that's exploring starts. But here we don't have to do that. And the third difference is the epsilon soft policy with the small probability of choosing the non-greedy action. So that's on policy MC control. Now we move to off policy MC prediction. So off policy MC control is omitted due to time constraints. So what's off policy? It means that you improve and evaluate a different target policy pi from the behavior policy B that's used to select actions. So the behavior policy may be more random and more adventurous than target policy to facilitate exploration. Could be a uniform random policy. So the behavior policy must cover the target policy. So if action is possible in target policy, it must also be possible in behavior policy. Otherwise, agent will never experience the SA pair. So for on policy, you improve and evaluate the behavior policy B that is being used to select actions. So the behavior policy is the same as the target policy. So importance sampling. So we want to estimate a expected value of a random variable x with distribution pi by sampling from another distribution rho. So the capital X is the random variable, small x is the sampled value for x. So by definition, expectation of a random variable based on distribution pi is sum of small x, a particular value, times its probability pi x for all possible x. So we assume the x is a discrete number. Otherwise, we need to use integrals. So and then you can do a switch of defined rho is pi xi over bxi for each xi, and then the sum is equal to b times rho times x. And then you can convert it into expectation over the distribution of b and rho times x, which is can be evaluated by sampling, drawing samples from the distribution B, behavior policy. So here we're discussing general random variables, not really reinforcement learning. So we compute expectation of random variable x with distribution pi by sampling from another distribution B, and then performing weighted average with weight rho x, where rho is pi over b for each xi. So let's look at one example. Say we have two possible distributions of a random variable x. With bx, you have with 85 probability, you have value 1, 5 probability of value 2, and so on. And pi x is another distribution among the 4 values. So we wanted to compute expectation of x with distribution pi. So we can simply compute it 0.3 times 1 and 0.4 times 2, and so on. So the expected value is 2.2. That's our ground truth. But we sample from B instead to evaluate the e pi x. So we draw the first sample from B. Suppose we get x is 1 with the probability 0.85. So the EBX, based on the formula, is only a single item, and rho is the pi xi over bxi, which is 0.3 divided by 0.85. That's rho. Yeah. So second sample, you get 3 with probability of 0.05. Then you add one more term of 3 times 0.1 divided by 0.05. And third draw, you get a 1 again. So you add another term here. So after 3 samples, you get a estimated expectation value of 2.24, which is pretty close to the ground truth of 2.2. So that's the idea of importance sampling. We'll see this idea again in policy gradients. So the basic concept is that you have the distribution B available and you're evaluating the expected value of x under another distribution pi. So you cannot simply do a average over your samples. You must do a weighted average. So coming back to reinforcement learning, we define a trajectory over behavior policy B as the sequence of starting from ST and the sequence of actions, the probability of the sequence of action state. And by using the Markov property, you can rewrite this term as a separate B term and P term, denoting the behavior of action selection and the environment state transition to the next state. And the rho term we saw before is probability of trajectory over under pi, the target policy, over the trajectory under B, the behavior policy, which is only difference is the pi here and B here. And these two terms cancel out. So we have this term. And for we can work backwards to compute more efficiently. So having the weighting factors, we can do off policy prediction. So remember the previous, we saw the MC prediction with Monte Carlo sampling. We simply generate episodes and average the returns for a particular state to get its value function, expected value function. But now we are doing the off policy MC prediction, which means that we are trying to evaluate a policy pi, but our behavior is has a policy B, different policy. Whereas in the previous on policy approach, you have the same policy to be evaluated and policy to be executed. But now we have a different behavior policy. As a result of this difference, we must add this weighting factor, W. By multiplying W to G before adding it, updating the G used for calculating the value function. And the W is computed based on backwards from episode, from the terminal state of the episode backwards, and multiplying a factor of for in a given state as K, you for the target policy, what's the probability of an action actually taken in the episode, divided by the probability of the action taken in the actual behavior policy. So that's the how you get W, and then then you multiply W to get a weighted average instead of the original just average to compute the value function. So it's called off policy because you're improving and evaluating a different target policy pi from the behavior policy B that's used to select actions. Therefore, you need to add the actual weighting The reason you want to do that is because the behavior policy may be much more random, more adventurous, which allows more exploration. Whereas you can, the target policy may become more and more deterministic as you are training your policy. Okay, any questions on Monte Carlo methods? Okay, so let's move on to TD learning. So let's first introduce the concept of exponential moving average. So running average update is, say you have a stream of incoming measurements of a variable x, and you need to update the average not by recomputing the average every time, but by keeping a running average. So you can define a weighting factor alpha, and every time you have a new measurement coming in, you weight it by alpha, and the old value weighted by 1 minus alpha. Or you can rewrite it as this form. So a shorthand notation is simply update the running average with a new value based on weight alpha. So if you write out this running sum, it's alpha times the most recent measurement xn plus 1 minus alpha, its previous average value, which can be written as recursively as alpha x n minus 1, the next recent measurement value plus 1 minus alpha, and so on. So if you take out it's xn plus 1 minus alpha of minus alpha squared. Am I missing something here? Xn is alpha xn. Oh, okay, okay, I got it right. So this should be alpha. And then is 1 over alpha is this guy. 1 over alpha is this guy. Yeah, so that's right. So so if you rewrite this moving average in this form, it clearly shows that it weights the more recent samples more. So the most recent sample has weight of 1. The next recent has weight of 1 minus alpha. The previous one has weight 1 minus alpha squared. So it gradually forgets about the past. So distant past values are wrong anyway for value function estimation. So it's not a simple average. So it's an uneven average. More recent values are weighted more than older values. So decreasing the learning rate alpha gradually can give a converging average. So TD learning, if you recall the Bellman expectation equation we saw before, if we solve it with dynamic programming, we need the P, the MDP model P. For TD learning, we're model free. We don't have the MDP model. So we evaluate the expectation by sampling. So expectation, here the two sums is replaced by a sampling. That is, capital R is the random variable. We're sampling from the random variable, plus gamma, capital V is the a random variable of the next state value function, and that's our target. And we are updating our running average running estimate of V with the new target value with a learning rate alpha. So the term target minus current value is the TD error. So ideally it should reduce to 0. So tabular TD, right now we are in a tabular world. We're not discussing neural networks yet. So comparing it to Monte Carlo, we saw before, Monte Carlo updates the value at the end of each episode, working backwards from the end of the episode, from the terminal state up to the starting state. TD updates a value at every time step. So this is called bootstrapping S from S prime. So you're estimating VS prime and then using the estimated value of VS prime to update the VS. So let's look at one example of a random walk. So this is a one-dimensional grid. Agent has uniform random policy W with equal probability of going left or right at every time step. Environment is deterministic. All episodes start in state C, the central state. Episodes terminate either on the left or on the right. Reward is 0 on all transitions except 1 for terminating on the right. So that's a good state. Discount factor gamma is 1, learning rate alpha is 0.5. So the value of each the state is the probability of terminating on the right when starting from state S. Based on the definition, based on the only reward you get of 1 of exiting on the right. So we can write the Bellman expectation equations. So set of Bellman expectation equations. So VA is on the left it's a 0 and it ends. On the right is VB. So 0 point it's 0.5 times VB, and transition itself has a reward of 0. VB has 2 possible choices, left or right. So it's 0.5 VA plus 0.5 VC, and so on. So VE has a 0.5 going into VD with reward 1 and 0.5 of going into the terminal state with a reward of 1. So I should make it more clear. Should be 0.5 c dot 1. So we can solve this set of linear equations to get the value functions shown on the figure. So suppose you run one episode from C to D to E to terminal to exit. Now based on TD, VC, you update the VC with the TD target, which is 0 plus gamma times the VD. All V's are initialized to be 0.5. So this guy has 0.5 as a result. That's after that's when you are in state C. When you are in D, you look ahead one step to see next state is E. So that's the RT plus 1 plus gamma times VE. And then you get 0.5. Next state VE, your next state is T, based on the trajectory, based on the episode. So now you have a reward of 1 by going into the terminal state. And VT itself is 0 minus 0.5, so you get 0.75. So that's the result of TD learning after this CDET trace. So for the Monte Carlo, at the end of the episode, you get a reward of 1, and that's your only reward. So that's also your returns. And then you update the values of CDE, that's all the states visited in the episode. So initially, initial value 0.5 plus alpha times 1, the return for the entire episode minus the old value 0.75. So CDE all have the updated value of 0.75. Now let's look at another episode based on starting from the end of the previous episode. Now we go from so every time you exit on the right, you return from to C and restart. So from C you go to D and E. Now at the state C, your TD update gets you 0.5 again. For D, your TD update gets you now the VE has changed before, right? VE last time we updated it to be 0.75. So now it's 0.75. And now the D's value is now 0.625. But for MC, the episode has not ended. And MC learns at the end of episode. So for MC, there's no update. So the values stay at 0.75 as before. Now the next sequence of part 2 of episode 2, you continue and you go E, D, C, you go left. Now for TD, a value of E is now the reward plus gamma times VD, because your next state is D now. You're going left. So plugging in the value for D, which is 6.625, you get a new value for E, 0.688. And from D, you go left, so your next state is C. The TD update gives you 0.563. But for Monte Carlo, again, no update because the episode is not ended. And then keep going, again, you go CDE. So from C, you update based on the next state of D. And from D, you update based on next state of E. So the TD update's next state is dependent on your direction of travel. And again, for MC, there's no update. So this example shows you that TD can perform more frequent updates than Monte Carlo, and it often converges faster. So here's an example of a random walk evaluated for MC. The red lines with different alpha learning rates and TD with different alpha. So TD generally converges faster than MC, but with higher learning rate, say alpha equals 0.15, error reduces faster but results in higher final error. So TD may converge the wrong value. That's the bias in machine learning. So larger alpha helps achieve faster convergence, but introduce higher bias. So here's the MC prediction for the mini grid world. We saw before. You have 4 episodes. Last time we used the 4 episodes for estimating a model, transition model. Now we are using it for estimating the value function, model free in the model free method. So in state A, you have a single state A. Where's it? A? That's the only one. So you exit with -10, so your value is -10. State D, you exit with +10, your value is 3 times. So you have times 3 divided by 3. For state B, you have you see it twice. So the first time the episode has reward of 8 -1 -1 10. Second time is also 8. So the average is 8. State C, now in the first 3 episodes, starting from C, C is not the starting state, but it's encountered in the middle of the episode, but that's okay too. So 3 of the episodes, it goes into D. 1 of the episodes, it goes into A. So its value is the average among the 4 episodes. And state E, it has once it goes north into C, but so once from E to C to D, another time is E to C to A. So its returns are 8 and -12. So the average is -2. So for policy evaluation, if we knew the MDP model, we can derive VB is equal to VE. but the MC predicted value functions are inaccurate due to limited sampling, because we're estimating V hat B is 8, whereas V hat E is -2, whereas they are symmetric. They shouldn't be different. The reason is that you're just unlucky for E, because for B, both episodes 1 and 2 start from B and end in D with a high value, whereas for E, you happen to see 2 episodes starting from E and ending in either D or A. So that's why the predicted values are not accurate. If we sample more data, then we can estimate more accurate values. So in general, MC learning, MC prediction is not sample efficient, since the value function of every state must be learned separately. It's not aware of the sequencing of the state. Yeah. So if we look at TD learning, say with the deterministic policy, we saw, say we have 4 episodes of BCD. Then based on the TD update, we can first update. We get transition from B to C. We get reward of -1, and the VC is 0. So and C to D, you get a reward -1 and a value of 10. So episode 2, the same BCD, you get you plug in the old value of -0.5, and you get updated values 1.5, 6.75, and so on. So as you're running, you keep updating the running average as your value function. So if you use in-place updates, in-place, no, I think this is not right. I shouldn't write this. Oh, okay. Yeah, let me delete this. The reason is that in-place updates is only for offline evaluation, where you can go backwards in a episode. But TD is an online method, so you cannot go backwards. You must, while you're in state B, you must update state B. You cannot wait until later. So yeah, I got confused here. This shouldn't be here. Yeah, so just to see this is still in place update. So if you have a higher learning rate, you converge faster. Yeah. So here's the backup diagrams for Monte Carlo. You are running all the way till the leaf, till the end of the episode, the terminal state, and then you do a backup along the path for all the states encountered in the episode. For TD learning, you are doing one-step backup with bootstrapping, backing up, updating the VST based on VST +1. For dynamic programming, you're doing a full backup. So looking up, you can see that so TD learning has shallow backup and sample backup. It's based on sampling. Whereas Monte Carlo is sampling and deep backup. You run till the end of the episode. Dynamic programming is a full backup, but it's also shallow. It's a one-step backup. Whereas exhaustive tree search, that's a full backup and deep backup. That's typically not feasible for complex systems. Okay, so yeah, I think we. Okay, I think now is a good time to stop. It's already 5 o'clock. Just to emphasize that this is a pretty important slide. So for Monte Carlo and temporal difference learning, both are model-free methods. So it's performing exploration. So it may have episodes like this episode goes this way, this episode goes this way, and so on. So you need to explore sufficiently to achieve a good learning result. Similarly for TD learning. Whereas for dynamic programming, the MDP planning we discussed before, there is no exploration. You are backing up. You're solving the recursive equations for all the states all the time. So it covers all the branches. Therefore, there's no issue of exploration for dynamic programming. Exploration is only for model-free methods like TD or MC. Okay, any questions? Okay, we'll stop here. See you next week. Goodbye.
Okay, see you. Bye.
Thank you. Bye.